Here we go. So lecture 10, this is the second part of the review for the midterm, which is on Wednesday during class time, 11 o'clock. And what problems would you like me to do from the review? Preferences? What do we got here? Well, let's take a look. All right, so there are problems on the pages 8, 12, 19. How far did I get last time? Should I start on page 45?
Let me check, Professor, how far you got in last lecture.
On page 45, it was numbers 1 to 6, 19, 20, and 21. On page 53, 1 and 2. On page 19, 1 to 6. Well, I didn't look my notes. That's interesting.
Professor, we stopped on page 19, exercise number 5,
Okay.
on last lecture. So, I don't know if you want to go, if you would like to go over, question 6 on page 19, or if you want to start on page 45 exercises.
No, let's look at number 6.
Okay, thank you.
Okay. Page 19. Oh, okay. So page 19, We're looking at n by n matrices. So this is page 19, number 6. And we're looking at the set of all square matrices, n by n matrices. And we want to prove its dimension is n squared. Well, a 2 by 2 matrix, for example, looks like A, B, C, D. And you can write that as A times the vector 1, 0, 0, 0, plus B times the vector 0, 1, 0, 0, plus C times the vector 0, 0, 1, 0, and D times the vector 0, 0, 0, 1. And with respect to these 4 particular matrices, every matrix is a linear combination. So every matrix, so a basis for the 2 by 2 matrices are just these 4 particular matrices: 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So this is a vector space of dimension 4, because there's a basis with 4 vectors. And if you looked at 3 by 3 matrices, so I can write them, let's say, A11, A12, A13, A21, A22, A23, A31, A32, A33. If you work with this a little bit, and by working, I mean spend an hour just writing down matrices and playing with them, expanding them, you could write this as A11 times the matrix with the 1 in the first position, first row, first column, and zeros everywhere else. And then A12 times the matrix, which looks like this, and so forth. And you'll get every 3 by 3 matrix as a linear combination of 9 matrices, where we could say the matrix EIJ, this is the 3 by 3 matrix with a 1 in row I, column J, and zeros everywhere else. And in exactly the same way, if you take an n by n matrix, A11, A12 up to A1n, A21, A22 up to A2n, down to AM1, AN1, AN2 up to ANN. This n by n matrix is a unique linear combination of the n squared sort of elementary matrices, EIJ, where EIJ is the n by n matrix with a 1 in row I, column J, and zeros everywhere else. So the dimension of this set of n by n matrices is n squared. And that's the whole proof of problem 6. Any questions about this? All right, let's look at the questions on page 45. We had page 45, numbers 1 to 6. So this is page 45. Number 1. So we have the two-dimensional vector space R2 and a function from T to R2 defined by a matrix, defined in this way, T of the vector XY is the vector XX. So this sends a vector in X in R2 to another vector in R2. And prove this is a linear combination. So suppose V1 is the vector. I'm going to write these as column vectors. Doesn't matter. You can use row vectors if you like. If V1 is X1, Y2, and V2 is X2, Y2, then V1 plus V2, when you add them, you add coordinates, you get that. So T of V1 plus V2, that's T of the vector X1 plus X2, Y1 plus Y2. And this gets sent to the vector where the first coordinate equals the second coordinate, equals this. X1 plus X2, X1 plus X2. And you can write this as the sum of two vectors, X1, X1, plus X2, X2. And X1, X1, this is T of the vector X1, Y1. And this is T of the vector X2, Y2.
Here's something I found on the web.
Oh,
According to Jiska.com,
hey.
the number 1 is a perfect square. 1 by 1 equals 1. And the perfect cube, 1 by 1 by 1 equals 1. Did that answer your question?
I'm in a room with an Alexa and somehow I thought I was asking a question. That's very funny. So this is T of V1 plus T of V2. So T of V1 plus V2 is T of V1 plus T of V2. That's the first condition that a linear transformation has to satisfy. What about T of lambda V1? If this is V1, lambda V1 is lambda X1, lambda X2. And this is T of the vector lambda X1, lambda X2. So that's lambda X1, lambda X1. That's exactly lambda times the vector X1, X1, which is lambda times T of X1, Y1, or lambda times T of V1. So these are the two conditions that a linear transformation has to satisfy, and it does. Any questions about this part of the problem? So this T is a linear transformation, and we want to find its kernel and its image. So this is T of XY equals XX. This is my linear transformation. By the way, geometrically, what does this mean? It means if you take a vector in the plane XY, it gets mapped onto the line Y equals X. It gets mapped to the point XX. So this linear transformation geometrically, if you take any point on the plane, it just projects it vertically up or down to the line Y equals X. In any case, we want to find the current, we want to show that T to the N equals T for all positive integers N. So let's look at T squared. T squared of XY, this means T of t of xy, t of xy is xx, and t of xx is xx. So that's t of xy. So t squared equals t. What about t cubed? T cubed is t composed with t squared. So t cubed of xy is t composed with t squared of xy. T squared of xy is xx, and t of xx is xx. So t cubed equals t. And in general, if t to the n is equal to t, then t to the n plus 1, that's t composed with t to the n, but t to the n is t, so that's t composed with t, which is t squared, which we already proved was equal to t. So by induction, if it's true for n, then it's true for n plus 1 means true for all n. Any questions about this? This is part B. Part C is to compute the kernel. So the kernel of T, or the null space of T, this is all vectors xy such that T of xy is 0. But this is all vectors xy. What is T of xy? Xx equals 0, which means it's all vectors xy where x equals 0. That is the set of all vectors 0, y. That's the kernel, which is what we call the y-axis, right? So all the points, all the vectors where x is 0, the y-axis. So every vector on the y-axis gets mapped by this function t, this linear transformation, to 0, to the origin. And that's the whole set of vectors that get sent to 0. And the image of t, well, that's the set of all t of xy, which is just xx. So this is just the line y equal x. This line y equals x, that's the image of t. Any questions about this?
Professor, did you write y equal to a times 0 or a times 0? I can't figure it out.
Where?
On C, you said x equal to 0 and then 0, y equal to a times 0. The line above that, the second to
here?
last line. Yes, yes.
This is y-axis,
Oh, okay.
right? That is this y-axis, that's the kernel of t. All right, that's a pretty problem. Let's look at number 2. Number 2 is another nice function. T from R2 to R2 defined by T of the vector XY. It moves the second coordinate to the first coordinate and makes the second coordinate 0. So we want to prove this is a linear transformation. So suppose again, we have V1 is the vector X1, Y1. V2 is the vector X2, Y2. So V1 plus V2 is the vector X1 plus X2, Y1 plus Y2. And lambda V1 is the vector lambda X1, lambda X2. So T of the sum of two vectors, that's T of X1 plus X2, Y1 plus Y2. You put the Y coordinate into the X position and make the second coordinate 0, which is Y1 0 plus Y2 0, which is exactly T of X1, Y1 plus T of X2, Y2, which is T of V1 plus T of V2. So this is a linear map. Sorry, satisfies the first condition for linearity. T of lambda V1 is T of lambda X1, lambda X2. Sorry, lambda X1, lambda Y1. That's lambda Y1 0, which is lambda times the vector Y1 0, which is lambda times T of X1, Y1, or lambda T of V1. So T is linear. It's a linear map, a linear transformation. So that's part A. Okay, almost part A. What is T squared of V1? That's T of V1. That's T of the vector T of X1, Y1. That's T of Y1 0. That is, you put the second coordinate first, and you made the second coordinate 0. Make the second coordinate first. Now this becomes 0, and it's 0, 0. So for any vector V, T squared of V is the 0 map. It's the function that sends every vector to 0. Okay, and now let's try to compute the kernel in the image. So the kernel of T is all vectors x, y, such that T of x, y is 0, which means the set of all vectors x, y, T of x, y is y comma 0, equal to 0 vector, which means all vectors where y is 0. Which is the x-axis. So the kernel is the x-axis. And what is the image? It's the set of all T of x, y, which is the set of all vectors of the form y comma 0, which is again the x-axis. So the kernel and the image in this case are the same. Kernel of T is the image of T is the x-axis. And geometrically, this is the line y equal x. Take the vector xy. If you reflect it through this line, you get the vector yx. Then you project it down to the x-axis, you get y0. So this is what the function t looks like that sends xy to y0. So again, you need to spend some time with these problems. Any questions before I go on to number 3? So page 45, number 3, we have linear transformation, again from R2 to R2. We have a matrix. Two minus 1 minus 4, 2. And we define a linear function, or a function, t sub a from R2 to R2 as follows. T of xy, you multiply the matrix A by xy. That's 2 minus 1 minus 4, 2 times xy. That's 2x minus y minus 4x plus 2y. That's the function. It sends a vector xy to this vector in R2. So for example, t of, I don't know, 3 minus 1 would be what? It would be x is 3, y is minus 1. It would be 2 times 3 minus minus 1. And this is minus 4 times 3 plus 2 times minus 1. So this is 6 plus 1. This is minus 12 minus 2. So you get 7 minus 14. That's the matrix A times this vector. Just to make sure that you can do these simple calculations, what is TA of the vector 5, 4? Just take a piece of paper and calculate this. You're taking the vector 2 minus 1 minus 4, 2, and multiplying it by the vector 5, 4. And what do you get? Can someone tell me the answer? When you multiply this, you get 10 minus 4 for the first coordinate, minus 20 plus 8. So this is 6 minus 12. What is TA of 0, 0?
Zero.
Yeah, 0, 0. Good. So I want to show this is a linear transformation. Let me just show it just. So this is a matrix calculation. And you need to work these things out at home over and over again with pencil and paper. You really need to spend a few hours doing these things. Suppose I have the two vectors, x1, y1, plus x2, y2. That's t sub a of x1 plus x2, y1 plus y2. That's equal to 2 x1 plus x2 minus y1 plus y2. That's the definition of this function. And minus 4 x1 plus x2 plus 2 times y1 plus y2. So if I just expand all this, this is 2x1 plus 2x2 minus y1 minus y2. And this is minus 4x1 minus 4x2 plus 2y1 plus 2y2. And that's supposed to be the same as TA of x1, y1 plus TA of x2, y2. Let's just check. What is this? It's this with x1 and y1, 2x1 minus y1 minus 4x1 plus 2y1. And then this applied to the vector x2, y2, 2x2 minus y2 minus 4x2 plus 2y2. When you add, you get 2x1 minus y1 plus 2x2 minus y2 minus 4x1 plus 2y1 minus 4x2 plus 2y2. When you check, these are equal, right? Because you can rearrange numbers, right? Same numbers. So, and in the same way, you can check that T of lambda xy is lambda T of xy. So TA is a linear transformation or a linear map. And we need to compute the kernel and the nullity, which means the dimension of the null space, and the image and the rank, which is the dimension of the image. So again, let me write this. TA of xy is 2x minus y minus 4x plus 2y. And when is that equal to 0? The kernel is all vectors xy, which get mapped to the 0 vector. So this is the same as saying 2xy minus y is 0, minus 4x plus 2y is 0. So we're solving two equations and two unknowns. These are the same equation, because if you take this equation and divide by minus 2, you get the first. So this is just a set of all vectors where y equals 2x. So the kernel of this, or the null space, and they mean the same thing, it's all vectors xy, where y equals 2x. That means all vectors of the form x, 2x. And this is exactly the set of all scalar multiples of the vector 1, 2. So this is the set of all scalar multiples, if you like, of 1, 2. So this vector is the basis for the kernel. And the dimension of the kernel is 1, because there's a basis with just one vector in it. So this is what is called sometimes the nullity of T.
So
So the
because
vector
it's
gets
one,
sent to
it's
0
just
if and
a
only
null?
if y equals 2x. So is there a question?
Oh, because it's one, it turns it into a null?
Uh, no.
Sorry.
So there's no null. I mean, null is not a word that we're using anywhere. There's the null space of a linear transformation, a linear map, which is all the vectors that get sent to 0 under the function, right? So, and what we calculated is a vector is mapped to 0. T sub a of a vector is 0 if and only if y equals 2x. So the line y equals 2x, that's this line in the plane, right? A map from R2 to R2 just sends every vector in the plane to another vector. And the vectors that get sent to 0 are all the vectors on the line y equals 2x. So the null space, or the kernel of this linear map, is this line, all the vectors on this line. And this is one dimensional, it's just a line. And 1, 2, for example, this vector is a basis for this one-dimensional subspace.
Okay, thank you.
And what is the image? So image of T. This is the set of all vectors. Let me write it maybe as all vectors A, B, such that T of xy equals AB for some vector xy in the space. That's the definition of the image of a map. So you take all the points xy and you see where they get mapped to. So this is all the vectors AB such that AB equals 2x minus y and B is minus 4x plus 2y for some vector xy in R2. But if you look at this, you see that all vectors AB, B is minus 2a. This vector is minus 2 times this vector. So this is a set of all vectors of the form A minus 2a, which is the set of all scalar multiples of the vector 1 minus 2. So that's the image of this linear transformation. All vectors, scalar multiples of 1 minus 2. The vector 1 minus 2, what's that? It's all the vectors on this line. This is the line. Oops, I didn't draw it very well. It should be up here. It's supposed to be the line y equals minus 2x. So the rank of this linear transformation, which is the dimension of the image, it's one dimensional. It's all scalar multiples of one vector. Are there questions about this? Again, this is, I don't want to say it's hard, but it's hard until you understand what's going on well. And that takes, some hours of work. Someone asked in the chat, if you do poorly on the midterm, can you recover? And the answer is absolutely yes. But the course doesn't stop at the midterm. So everything that's on the midterm is required to, you need that to understand what comes later. So you really have to try not to fall behind. Then we do problem number 4. We have a matrix, 1, 2, 3, 4. And the linear map T sub A of x, y, defined by what you get when you multiply the matrix A times x, y. 1, 2, 3, 4 times x, y. When you do matrix multiplication, you get x plus 2y, 3x plus 4y. So this is my linear map. For example, T sub A of 2 minus 1 is what? When x is 2 and y is minus 1, you get this. That's 2 minus 2, 6 minus 4. This is 0, 2. So 2 minus 1 gets sent to the vector 0, 2, for example. It's hard to draw a picture of this linear map. It's much more complicated. What's the kernel? The kernel is the set of all vectors x, y, such that T sub A of x, y is 0. That means all vectors x, y, where the vector x plus 2y, 3x plus 4y equals the 0 vector. So vectors in the kernel, if the coordinates satisfy these two equations and two unknowns, x plus 2y equals 0, 3x plus 4y equals 0. For example, if you take the first equation and you multiply it by minus 2, you get minus 2x minus 4y equals 0. The second equation is 3x plus 4y equals 0. If you add, you get x equals 0. So x has to equal 0. And if you plug in x equals 0, you get y equals 0. So the kernel of this linear map consists just of the 0 vector. The only vector that gets mapped to 0 is 0, 0. So the dimension of the kernel is 0. This is just the trivial subspace that consists of just the 0 vector. And what is the image? Well, first of all, we know that the dimension of the kernel of a linear map plus the dimension of the image equals the dimension of the vector space. So in this case, the vector space is R2. And the dimension of R2 is 2. So if you plug in the numbers, the kernel of T has dimension 0. So that plus the dimension of the image, which is called the rank, has to equal the dimension of the space, which is 2. So the rank of T is 2. So the image of T sub A This is a two-dimensional subspace. In R2, but R2 is dimension 2, so this is all of R2. So every vector is in the image. The image of this linear map is all of R2. If you want an alternate proof, you want to ask, so if you have a vector AB, find, if you can, XY such that T of XY is AB. That means we want to solve, can we solve the equations x plus 2y equals A, 3x plus 4y equals B? Given A and B, can we solve these two equations and two unknowns? So again, if we take the first equation and multiply it by -2, you get minus 2x minus 4y is minus 2a. If you add, the y's cancel, you get x is equal to b minus 2a. And if x is b minus 2a, 2y is a minus x, is a minus b minus 2a, is 3a minus b. So y is 3/2 a minus 1/2 b. So if this calculation is correct, T of xy is going to be, sorry, it's going to be T of b minus 2a, 3/2 a minus 1/2 b. So that's b plus 2y, that's b plus 2 times this, 3a minus b. Sorry. B minus 2a and 3a minus b over 2, so that's x, b minus 2a plus 2 times 3a minus b over 2, and 3x plus 4 times 3a minus b over 2. So this is b minus 2a plus 3a minus b. First coordinate is a. This is 3b minus 2b is b, and minus 6a plus 6a. You get ab. So this is maybe a little bit hard to read, but in any case, you have to learn how to do this calculation yourself. So the image is the whole space, and the rank is 2. Right, so these are really very important problems.
Professor,
Look at number 5.
Professor.
Is there a question?
Yes, matrices, they are on the midterm exam, right?
Sorry?
The matrices, are they on the midterm exam?
Yes. So this is still on page 45, number 5. So here we have a complex vector space, just like R2, except the numbers are complex numbers instead of just real numbers. And T of xy sends the vector xy and multiplies the first coordinate by I, and it changes the sign of the second coordinate. Why is this a linear transformation? Well, V is x1, y1, and V2 is x2, y2. It's the same calculation, T of V1 plus V2. When you add these vectors, that's x1 plus x2, y1 plus y2. You multiply the first coordinate by I, and you change the sign of the second coordinate. This is ix1 plus ix2 minus y1 minus y2. I can write this as the sum of two vectors, ix1 minus y1, ix2 minus y2. This is T of x1, y1, and this is T of x2, y2. Exactly the same. And the same calculation shows that T of lambda V1 is lambda T of V1. And then the next part is to prove that if you iterate this function 4 times, you get the identity. So let's see what happens. You take the vector xy, these are complex numbers, you apply t, you get ix minus y. Apply t again, you multiply this by I, you get I times ix, and minus y. I times ix, I squared is minus 1. This is minus x, and this is plus y. Apply t a third time, multiply this by I, change the sign of this. And one last time, the fourth time, apply t, you get I times minus ix and minus y. This is minus I squared xy. My I squared is minus 1. Minus 1 times minus 1 is plus 1, so this is just x. And minus times minus is plus. So when you do this 4 times, t to the 4th brings you back, applied to the vector xy, brings you back to xy. So t to the 4th is equal to the identity. Problem 6 is very similar, only easier. Here we have t from R2 to R2, and t of xy is just yx. And y is t squared equal to the identity. You take the vector xy and you apply t, you flip the coordinates. xy goes to yx. If you apply t again, you flip the coordinates, yx goes to xy. So you're back where you started, and t squared is the identity. Any questions about any of these? I also assign 19, 20, and 21. So let's look at those. So G is a map from R3 to R3, defined by T of the vector X, Y, Z goes to X, Y, 0. So if you think of this as in three-dimensional space, which it is, this is the X, Y, and Z coordinates. If I take a vector E1 of length 1 in the X direction, T of the vector 1, 0, 0 is 1, 0, 0. If I take a unit vector in the Y direction, T of 0, 1, 0 is 0, 1, 0. This is the way you usually write them in calculus or physics. I take a unit vector in the Z direction. When X and Y are 0, this gets sent to 0. So this vector is sent to itself, this vector is sent to itself, this vector goes down to 0. So in fact, the image of this linear map is just the XY plane. All you do is you take a vector and the map projects it down into the XY plane. If we wanted to write this as a matrix, we could take the matrix 1, 0, 0, 0, 1, 0, and 0, 0, 0. Because A applied to the vector X, Y, Z, it's 1, 0, 0, 0, 1, 0, 0, 0, 0, applied to X, Y, Z. When you multiply this matrix times this vector, you get X, Y, 0. So the standard basis for R3 are these three vectors. E1 is 1, 0, 0. E2 is 0, 1, 0. E3 is 0, 0, 1. And this is T of E1. This is T of E2. This is T of E3. Let me get this matrix. I mean, geometrically, you can see by when you look at this picture hard enough what the image and the kernel are. The image is just the XY plane. Every vector gets mapped to the XY plane, and the kernel is the Z-axis. The vectors that get mapped to 0 are just the vectors on the Z-axis. And if you wanted to work this out sort of carefully, the kernel of this map, it's all X, Y, Z, such that T of X, Y, Z, which is X, Y, 0, is equal to 0, 0, 0, which means it's a set of all vectors, X, Y, Z, where X equal Y equals 0. That's the set of all vectors, 0, 0, Z. Just the Z-axis. And the dimension of the kernel is 1. This is a one-dimensional space. And the image, it's all vectors X, Y, 0. That's the XY plane. And the dimension of the image, the rank, is 2. And the theorem that says the dimension of the kernel plus the dimension of the image equals the dimension of the vector space says 1 plus 2 equals 3. It's indisputable. Any questions about this? And this is the basic linear algebra in our textbook. Completely fundamental stuff. All right, no question? Let's look at problem 20. We have a function from 4-dimensional space to 2-dimensional space defined by t of x1, x2, x3, x4 equals x1 plus x2, x3 plus x4. So the standard basis for R4 is E1 is the vector 1, 0, 0, 0. E2 is the vector 0, 1, 0, 0. E3 is the vector 0, 0, 1, 0. And E4 is the vector 0, 0, 0, 1. And what is T of E1? It's T of 1, 0, 0, 0. X1 is 1, the other coordinate is 0. This is 1, 0. T of E2 or T of 0, 1, 0, 0. X2 is 1, the other coordinate is 0. This is also 1, 0. T of E3, 0, 0, 1, 0. X1, X2, X4 is 0, and X3 is 1. This is 0, 1. And T of E4, or T of 0, 0, 0, 1. This is X1, X2, X3 are 0, X4 is 1. This is 0, 1. And the matrix for T is it's going to send a 4-dimensional vector to a 2-dimensional vector. So it's going to be a 2 by 4 dimensions, and 1, 0, 1, 0, 0, 1, 0, 1. Because if you apply this to x1, x2, x3, x4, you get x1 plus x2, x3 plus x4. So this is the matrix for this linear transformation. And what is the kernel? So T of x1, x2, x3, x4, which is x1 plus x2, x3 plus x4, that's the 0 vector if and only if x1 plus x2 equals 0, x3 plus x4 equals 0, which is the same as x2 is minus x1 and x4 is minus x3. So a vector in the kernel is going to have x1 minus x1, because x2 is minus x1, x3 and x4 is minus x3. I could write that as x1 times the vector 1 minus 1, 0, 0, plus x3 times the vector 0, 0, 1 minus 1. And every vector in the kernel is uniquely a linear combination of these two vectors. So the dimension of the kernel is 2. And the dimension of the image is 2 because 2 plus 2 is 4. Also, you can get every vector in this form. Questions? Okay. Let's go to number 21. So we have a linear transformation from R4 to R3 defined by T of x1, x2, x3, x4 equals x1 plus x2, x3 plus x4, x1 plus x2 plus x3 plus x4. So for example, T of your first standard basis vector 1, 0, 0, 0. When x1 is 0 and the other coordinates are, when x1 is 1 and the other coordinates are 0, you get 1, 0, 1. T of E2, that's the vector 0, 1, 0, 0. When x2 is 1 and everything else is 0, you also get 1, 0, 1. T of E3, which is the vector 0, 0, 1, 0. X3 is 1 and everything else is 0, you get 0, 1, 1. And T of E4 is 0, 0, 0, 1. X4 is 1 and everything else is 0, you get 0, 1, 1. So the matrix for this linear map, you can say, is 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1. And you can check, you apply this to the vector x1, x2, x3, x4, you get exactly this vector. What's in the kernel? So T of x1, x2, x3, x4, which is x1 plus x2, x3 plus x4, x1 plus x2 plus x3 plus x4, that's equal to the 0 vector if and only if x1 plus x2 equals 0 and x3 plus x4 equals 0. And this condition, but this follows from these two. So if and only if x2 is minus x1 and x4 is minus x3. So the kernel of T is all the vectors x1, x2, x3, x4, but x1, x2 is minus x1, x3 and x4 is minus x3. Looks very similar to the preceding problem. Not exactly the same, but similar. And this is x1 times the vector 1, minus 1, 0, 0. And x3 times the vector 0, 0, 1, minus 1. So this kernel is two-dimensional. Every vector is a linear combination of these two vectors. So a basis for the kernel, or the null space of T, are the two vectors 1, minus 1, 0, 0, and 0, 0, 1, minus 1. So the dimension of the kernel is 2. What about the image? So remember, T is this linear map. So the image is all vectors A, B, C, such that A, B, C is T of x1, x2, x3, x4 for some vector in R4. This is all vectors A, B, and C, which can be written in the form x1 plus x2, x3 plus x4, x1 plus x2 plus x3 plus x4. So the question is, when can you solve the equation x1 plus x2 equals A, x3 plus x4 equals B, x1 plus x2 plus x3 plus x4 equals C? But x1 plus x2, x3 plus x4, this equation implies that A plus B equals C. And in fact, whenever A plus B equals C, I can choose x2 and x4 to be 0, x1 equals A, x3 equals B, and I get this. So the image of T is all vectors of the form A, B, A plus B, which is all vectors of the form A0, A plus 0, BB, which is A times the vector 1, 0, 1 plus B times the vector 0, 1, 1. And these two vectors are linearly independent, so they form a basis for the image. And so the dimension of the image of T is 2. And the dimension of the kernel of T was also 2. And the dimension of R4 is 4, and we get 2 plus 2 equals 4. Nullity, dimension of the kernel, rank, dimension of the image, equals the dimension of the space, R4, 2 plus 2 equals 4. So this is a check that everything we did looks okay. Okay. Lot to mull over. Then there were 2 problems on page 53. Let's take a look at them. So we have this very simple looking map T from R2 to R2 defined by T of the vector XY is 5x minus y and 3x plus 2y. Actually, just to make life simple, I'll come back to this, but this won't be on the exam. And I'll talk about this next week, these types of problems. Instead, maybe what I'll do is go back and look at the problems that I didn't get to record last week. So this was on page 19, the first couple of problems. So page 19.
Oh, Professor, I'm sorry to interrupt, but did you just say page 53 won't be in the exam?
Correct.
Okay.
Let's go back and so page 9 or page 8, let's take a look. Yeah. Okay, sorry. Page 8. So we have in R2 the subsets W1 with all vectors where the second coordinate is 0. W2 is the set of all vectors where the first coordinate is 0. And W3 is the set of all vectors where the first coordinate equals the second coordinate. I want to show these are subspaces. Well, if you take a vector T1, 0 and a vector T2, 0, and you add them, you get this vector. So if you take two vectors where the second coordinate is 0, their sum still has the second coordinate of 0. And lambda times T0 is lambda T0. So these two facts together mean W1 is a subspace. It's closed under vector addition and scalar multiplication. And the same holds for the other two subspaces. If I take 0T1 plus 0T2, that's 0T1 plus T2. And lambda 0T is 0 lambda T. So if I have two vectors with the first coordinate 0, so is their sum, and so is any scalar multiple. So W2 is a subspace. And if I look at W3, if I take two vectors with the same first coordinates and second coordinates, get T1 plus T2, T1 plus T2, same coordinates. And lambda times TT is lambda T, lambda T. Again, same coordinates. So W3 is a subspace. Any questions about that? If I take any vector T1, T2 in R2, T1, T2 is T1, 0 plus 0, t1, 0, t2. And this is the sum of a vector in W1 and a vector in W2. And this representation is unique. The only vector that's in both of these subspaces is the 0 vector. So R2 is in fact W1, direct sum with W2. And if I look at W1 plus W3, maybe I have to be a little bit more clever. If I take T1 and T2 in R2, I can write that as the vector. I want to write it as a vector where the first coordinate is 0. Where the second coordinate is 0, and a vector where the two coordinates are the same. So the two coordinates the same have to be T2, T2. If I let this be T1 minus T2, 0, you add these two together, this is what you get. And this is in W1, and this is in W2. And this is unique. There's no other way to write a vector as a sum of W1 plus W3 other than this, and this becomes a direct sum. The only other interesting part is part D. If I take a vector T1, T2, I can write this as T1, 0 plus 0, T2 plus 0, 0. This is in W1 plus W2 plus W3. But I can also write it as, let's say, T1 minus 1, 0, T2 minus 1, and 1, 1. First coordinate 0, second coordinate 0, first coordinate 0, coordinates the same. This is also in W1 plus W2 plus W3. So I have two different representations of a vector as a combination, as a sum of vectors from these three spaces. And if I can do it in two ways, it means I don't have a direct sum. So R2 is not W1 direct sum W2, direct sum W3. It's not, because I can write a vector as a sum of the vectors in each of these three spaces in two different ways. Any questions about that? Oops. What happened here? Let's look at number 2. In R3, I have the subspaces TT0, that is all vectors. This is shorthand, but it's written down in the notes, so I don't have to be more so careful. All vectors where the first two coordinates are equal. W2 is all vectors where the first and third coordinates are equal. W3 is all vectors where the second and third coordinates are equal. So you can check, just as I did already many times, that these are all subspaces. And suppose I want to write a vector x, y, z as a sum of vectors from each of these subspaces. So let's say T1, T1, 0, T2, 0, T2, 0, T3, T3, which is T1 plus T2, T1 plus T3, T2 plus T3. So this is possible if and only if I can solve the equations T1 plus T2 equals X, T1 plus T3 equals Y, T2 plus T3 equals Z. I have to solve 3 equations and 3 unknowns. The unknowns of T1, T2, T3. So you solve this the way you did in high school. You take the second equation and subtract it from the first. You get T2 minus T3 is X minus Y. Second equation says T2 plus T3 is Z. If I add, I get 2T2 equals X minus Y plus Z. So T2 is all this over 2. And I can continue to solve for T1 and T3, and I get a unique solution. So there exist unique numbers, T1, T2, T3, such that this equation is satisfied, which means that R3 is the direct sum of these subspaces. Problem 3 is exactly the same as problem 4. So if we go on to problem number 5. Sorry, problem number 4. We have W1 is the set of all linear all scalar multiples of a vector AC. W2 is the set of all scalar multiples of a vector BD. And we want to prove that R2 is the direct sum of these subspaces if and only if AD minus BC is not 0. So the question is, when can we solve, given a vector XY, when can we write this as some linear combination of AC and BD? Because if you add these vectors, this is AT1 plus BT2, CT1 plus BT, 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 T2. So it means, when can you solve these two equations and two unknowns? The unknowns are T1 and T2. Maybe to make this less ambiguous, I write this RS. So you want to solve the equations AT1 plus BT2 equals R, and CT1 plus BT2 equals S. So let's just solve the equations. If we eliminate T2, I can take the first equation and multiply it by D. I can take the second equation and multiply it by B. Subtract, I get AD minus BC T1 is DR minus B sub S. So if AD minus BC is not 0, I can divide by it, and I get a value for T1, and similarly, I get a value for T2. So if this condition is satisfied, every vector is a linear combination of a vector in W1 and W2. But if this is equal to 0, I can't always solve this equation. I only can solve it if this is 0, which is not typically the case. So that is briefly the solution to the problem. Okay. That's it. Any questions? Yes. you've grown up beyond calculus. And someone asked me if there's any tutoring on campus for linear algebra, and I double checked with the math department, and the answer is no. I mean, there's a math lab that tutors, but it doesn't tutor any advanced classes. It stops basically at calculus. So that's just the story. Again, I remind you, there are office hours today and tomorrow. And there are actually 2 office hours tomorrow, one in the afternoon or in the morning, I forget. The other in the evening. It's on Blackboard. So I encourage you to stop into one of these problem sessions if you want to ask questions. If not, then we're done for today, and the exam is 11 o'clock on Wednesday. Take care, all.
Monday or Wednesday, sir?
The exam is Wednesday, 2 days from
Okay.
today.
All right. Thank you.
The lecture will be uploaded, and as soon as I log off. Takes a while with YouTube, but you know, I don't know, 5 or 10 minutes, whatever it takes. Okay. Bye, everybody.